For this problem, we're going to imagine 0.2 moles of hydrogen atoms. We're excited and then relax from the n equals 5 to the n equals 1 and emit all of that energy as photons. Their container around them absorbs it all, and that container has a heat capacity, not a specific heat capacity, so we don't need to know the mass. We just general heat capacity for the sum of all the stuff that says 3.105 kilojoules of energy is required to raise it 1 degree Celsius. Given this, what is my delta T for the container, and what is the energy of this photon? Go ahead and pause, see if you can solve it, and come on back. All right, if you're back, well, to determine delta T, I'd be looking at a Q equals, now normally we think mass specific heat delta T, but if you just combine those two, you get a general heat capacity. So this is really a heat capacity delta T. We were given our general heat capacity. We want to solve delta T, which means I need energy. I need that total energy. Well, the energy is coming from the photons. My real first step is I have to solve the energy of the photons, and then I can figure out, well, what's my total energy that comes from 0.2 moles of the hydrogen atoms. So what is my energy of my photon? Well, energy equals hc over lambda, and I know that 1 over lambda is equal to the Rhydberg constant, 1 over n1 squared minus 1 over n2 squared. If I want that wavelength, and all I know is hydrogen's relaxing orbitals, the only way to get the wavelength is go through the Rhydberg equation. Which means if I can get 1 over the wavelength, I just need to multiply it by hc to get the energy. To find the Rhydberg then, remember that RH is 109,678 per centimeter times, well, we're going to go down to 1 squared. We're going to start up at 5 squared. So the difference is going to be 1 minus 0.04. So 0.96 is going to be our difference. We're going to get the vast majority of the energy that comes from the Rhydberg constant, which is going to be 9.497 times 10 to the minus 8 meters, or 95 nanometers. I have my wavelength. Well, hc over my wavelength is my energy, so 6.626 times 10 negative 34 joules seconds, 3 times 10 to the 8 meters per second, 9.497 times 10 to the minus 8 meters. I can solve my energy of that photon, which is going to give us 2.093 times 10 to the minus 18 joules. The energy of our individual photons is pretty energetic, a little bit more normal visible light, which at 94 nanometers is a little smaller than visible light in terms of wavelength. So this holds up with what we expect. Total energy then is equal to this energy per photon times the number of photons, which, well, each hydrogen relaxes 1 electron, so 0.2 moles. 2.093 times 10 to negative 18 joules. We really only have per photon, and there are 6.022 times 10 to the 23 photons in 1 mole. So we'll get our amplification to a mole, but we really want 0.2 moles. So we'll shrink it back down a little bit. Moles will cancel, photons will cancel. We'll get the joules for this, and it's 252078 joules, or 252 kilojoules. Well, that's the total energy from all of our photons. So Q equals our calculation here again. 252 kilojoules is going to equal 3.105 kilojoules per degree Celsius times the delta T. Divided over my delta T is going to equal 81.2 degrees Celsius. We will heat up our object by approximately 81.2 degrees Celsius. Now, obtaining 0.2 moles of excited hydrogen is effectively impossible at a single moment. They are continuously excited and released. This would be something you'd really do over time, like a microwave. But we can do the calculation for what amount of energy it would release when a total of 0.2 moles of hydrogen atoms have successfully released their energy from n equals 5 down to n equals 1.